Hello. Can you hear me? Hello, can you hear me? I cannot hear you. Hello?
Hey Maya, we can hear you.
Oh, excellent, wonderful. All right, let me just. I'll just try a share. How's that?
Yes, we can still see your screen.
Perfect, okay.
Okay, all right. So Maya, we are going to share some of our slides first, and at 12:30 your time, 2:30 sharp, we will I'll introduce you, and after about a minute, you start sharing your slide.
Fantastic, thank you.
Okay, thank you. People can hear me, right? Okay, it's time. Let's get started. Good morning and good afternoon. Welcome to workshop number 2. So many of you have joined. I'm honored to introduce our special speaker today, Dr. Maya Petersen. Dr. Petersen is Associate Professor of Biostatistics and Epidemiology at the School of Public Health of University of California, Berkeley. Her methodological research focuses on the development and application of novel causal inference methods to problems in health, with the emphasis on longitudinal data and adaptive treatment strategies, machine learning methods, and on study design and analytic strategies for cluster randomized trials. She is currently lead statistician for a large HIV prevention trial in East Africa, is co-PI of a sequential multiple assignment randomized trial to optimize retention in HIV care, and is a co-investigator on the international epidemiological databases to evaluate AIDS for Eastern and Southern Africa, large HIV clinical trial data consortium. Her course, Introduction to Causal Inference, joined with Laura Baza, was awarded 2014 American Statistical Association's Causality in Statistical Education Prize. She has a strong interest and published extensively at the interface between biostatistics, epidemiology, and clinical medicine, and is deeply committed to strengthening communication between stakeholders surrounding the complexity of causal inference methods. Her workshop today is titled Targeted Maximum Likelihood Estimation, Integrating Machine Learning to Evaluate the Effects of Longitudinal Interventions. The workshop provides an introduction to implementation of TMLE with superlearning, illustrated using applied case studies from HIV implementation science. Please send in your question via Zoom Q&A or chat functions at any time during the workshop. Maya will answer them during the designated Q&A session today. Without further ado, please join me to welcome Maya.
Oh, right. Ooh, I've got an echo. Let's see. There we go. Full screen. Bring my shared window to Hold on. I think people cannot see. Hold on. Let me try this again. Share. Desktop. Let's try that. Share. All right. How is that? I think that should be good. Okay, well, excellent. Thank you so much for that lovely introduction, Yi. And this is really just a pleasure to do this. And it's always fun to teach in person because you can see people's faces. Oops, hold on. Let me just make sure there's a chat. Hold on, chat. How is that? Oh, people are asking now. So just send me a chat if all is well and I will get going here. Okay. All is well. Excellent. Okay, thanks so much. So anyway, a pleasure to have this opportunity. Thanks so much for the introduction, and I'm really looking forward to just this chance to talk a little bit about some of the methods that I both enjoyed teaching and also we really found helpful in our study, in our applied work. And in particular, as you mentioned, I do applied work really looking at prevention and treatment of HIV in East Africa. There we go. So just as a little bit of background to ground our discussion today, I'll try to move this guy out of the way. All Just a little bit of background to ground our discussion today. I'm going to be talking about a couple of case studies drawn from my work on HIV prevention and treatment and really HIV implementation science in East Africa. So clearly these methods are widely applicable across all sorts of health sciences and really social sciences and many other types of work as well. But just to ground ourselves, I'll be talking in particular about work looking at ways to improve retention in HIV care in sub-Saharan Africa. So just as some brief motivation, a reminder that we're making great progress against the HIV epidemic, but much work still to be done. And really a lot of the burden of disease is borne by sub-Saharan Africa. And it's also, so we need to find better ways of treating HIV in this context, really in the context as well of limited financial and human resources. So in particular, I'm going to give a couple of case studies that look at ways to improve retention in HIV care in East Africa and use those to motivate and also step through some of these causal inference methods. So this is just why would we care about HIV, retention in HIV care in East Africa. So first, that lost HIV care is extremely common. So what I mean by lost HIV care, a patient is being seen in clinic and then for a multitude of reasons drops out of care. And there's been a lot of work showing that this loss to care or retention failure is associated with very high mortality. So here's just some plots of survival following drop or mortality following loss to HIV care at a number of clinics in sub-Saharan Africa. So with that as motivation, we're going to look at two sort of related case studies to step through our introduction to these causal inference methods. And so in particular, we're going to look first at an example in which we, this is real data drawn from East Africa, where we attempted to estimate the effect of a nurse-based triage system on retention to care. And this is the reference that was given, one of the references or teaching materials that was given by Yi on the, in the introduction to the course. So we're going to use that for a few reasons. So I know that there's a lot of interest in particular, methods for estimating the effects of longitudinal interventions or interventions that can change over time, and in particular, longitudinal dynamic regimes. But I think in order to really introduce the methods that I want to talk about, and in particular, TMLE and double robust efficient methods, I think it's a lot easier to kind of build up to it slowly with a review of essentially how do we tackle easier problems in this context. And then, so we'll begin by just giving an overview of what we sometimes call the causal roadmap, using this example as a motivation, but just reviewing how we might tackle an easier version of the question in the point treatment setting, where we only care about an intervention at a single time point. And then we'll build on that, and that'll give us a way to sort of get our hands around what are some of the estimators that are available to us, and also what does TMLE actually do. We'll build on that and extend it out to look at how would we estimate the effects of longitudinal interventions in this setting. And we'll talk about some implementation choices and also show some data and simulation results. And then finally, I'll just talk a little bit about challenges and ongoing work. So these are hard problems. I think there's been amazing progress made by many people in recent years, and it's fun to have this chance to share some of that. But clearly there's always more work to be done. And so try to just highlight some areas where there's still real challenges and some ongoing work. I'll note as well that in this, as I step through this case study, I'm really going to use slightly simplified version of the longitudinal causal effect that we went after in the materials in the paper that was shared prior to the course, just because it simplifies the didactics a bit, and we're squeezing a lot into this 2-hour session. But I do encourage you to have a look at those papers, and all of the code available implementing the analysis in those papers is available in GitHub. And you can link to it from the papers. So we'll use that to sort of build up to how do you use longitudinal TMLE in the context of time-varying intervention. We'll give some examples of how this can actually be implemented using the LTMLE-R package, as well as there's links to more extensive examples with that. And then we'll move on in the second part to a related example where, again, what we're aiming to do is learn better ways to keep patients retained in HIV care. But the second example is really motivated off of a sequentially randomized trial that I co-PI that Yi mentioned at the beginning. So we'll use that to talk about how we can take what we've learned for time-varying treatments and extend that to dynamic treatments, dynamic time-dependent time-varying treatments. And what's nice is all the work that we do to build up estimators for those longitudinal static treatments, we can really apply fairly directly to time-varying dynamic treatments. And then depending on time, I'm going to talk a little bit about one set of methods for going after particularly optimal dynamic treatments and what those are. All right. So to start off then, let's look at our first case study. So this is a case study where there's a lot of interest in studying whether task shifting of HIV care for clinically stable or low-risk patients with HIV, whether moving their care from clinicians to nurses might benefit them, as well as in sort of secondary questions benefit other patients in the clinic. The motivation for this really is the fact that there are truly limited human resources, and so with some of this task shifting, if it was done appropriately for patients who would do just as well with clinically with someone trained as a nurse, this could be beneficial because patients could receive essentially more time, more one-on-one attention, et cetera. And so this was studied in observational context using clinical cohort data in which a subset of low-risk patients, so clinically stable patients at a number of HIV clinics in East Africa were enrolled at varying but non-random times into this task shifting program following their eligibility. All right. So we're going to use that then as a way to step through the basic causal inference roadmap for a point treatment problem to begin with, motivated by that case study, and then extend that out to a longitudinal problem. So this is the causal roadmap, and I teach with this structure, and I have to say I found it incredibly helpful, both in teaching these methods, but really in tackling my own applied problems. I think it's a very useful structure for thinking about causal inference because it helps you keep the different pieces of the problem or the challenge separate. It helps you keep from mixing up questions of defining your target causal question, from figuring out whether you actually measured enough to answer that causal question, to figuring out how to estimate the resulting statistical parameter. And so we're going to step through that in the point treatment setting. All right. So in particular, I'm just going to give an overview of what these steps are, again, because I think they're invaluable, before moving on to the case study. So first step in the roadmap, we're going to talk about specifying a causal question, in particular as a parameter of counterfactual distributions. And I understand, you know, this is the latest in sort of a long series of outstanding workshops, CIMPOD workshops led by PCOR. And so I think a lot of this early stuff will be familiar to you, but I still think it's just worth reviewing to make sure we're all on the same page. So we'll specify a causal question as a parameter of counterfactual distributions. We're going to specify our observed data and our statistical model. Using a specific definition of a statistical model, really in its formal sense, the set of possible observed data distributions. Then we're going to tackle this step of identification. So in other words, translating our causal parameter into a parameter of our observed data distribution, or a statistical parameter, or an estimand. And we can do this under explicit causal assumptions. And these are assumptions that can be expressed in the language of graphs or counterfactuals. And I think most people on this call will have seen all of this before, particularly in the point treatment setting. Then finally, once we've done that, we have an estimand, or a statistical target parameter, a parameter of the observed data distribution. We have a statistical model, or a set of possible observed data distributions, and that lands us at a statistical estimation problem. So all of the steps up to here really benefit from using this formal causal framework, but once we get to step 4, we are fully in the land of statistics. So now we have a statistical estimation problem, and we can think about different statistical estimators. So particular in this talk talk today, the focus is going to be on a double robust estimator, targeted maximum likelihood estimation, but I'm also going to do a quick review of a couple of other types of estimator, inverse probability weighting and parametric G computation, mainly because I think building up with these really makes it easier to understand TMLE. I would also note that coming up, Jessica Young in a few weeks in the next workshop is going to give a really nice in-depth presentation on parametric G computation for longitudinal dynamic regimes. So we'll talk a little bit as well about, this is a statistical problem. We can talk about different statistical estimators, and in particular, those estimators will have different statistical properties. So we'll talk a little about that. So to set up then with our case study, we want to define a few things starting out. So to start off with, we could say, what's our causal question? So we're going to talk about our time scale. So here we're going to use a 90-day time scale. So essentially we're discretizing time into 3-month segments. And our baseline is going to be the date at which a subject is first eligible for enrollment into this LREC or task shifting program. Then next, we'll talk about, the next element of the data that's important is the intervention. So this is sometimes called in the literature the intervention, the exposure, the treatment. We're going to use a convention that you see in a lot of the causal inference literature and call that guy A. And A, to start out with for us, in this simple point treatment study, is just going to be an indicator if you enrolled right away, so in the first 90 days, into this LREC program. So with that, then, we can talk about counterfactual outcomes. So our outcome here is whether you're retained in care 18 months after your initial eligibility. And we can talk about your counterfactual outcome or your counterfactual retention status 18 months later under immediate enrollment, so A is 1, or under deferred enrollment, so A is 0. And we're going to use this parentheses here to denote the counterfactual outcome. And then finally, we can talk about a target causal parameter, so translating our question into a formal parameter of the distribution of these counterfactual outcomes. And so here is an example. We can look at the average treatment effect. So this is just the difference in the proportion that would be lost to care if everyone enrolled immediately versus everyone deferred enrollment. And so this is obviously a function of the expectation of the counterfactual outcome under A is 1, and the expectation of the counterfactual outcome under A is 0. And so just to simplify things in the next slides, we'll just talk about identifying and estimating one piece of that, EYA, and you can just substitute in a 1 or a 0 there and get back to the average treatment effect. So we've specified our target causal parameter. Now we want to specify our observed data and statistical model. So in this case, our observed data consisted of 15,225 copies. I'm going to say their IID for here. We could come back to that in the Q&A session. This is essentially for didactic purposes in the talk, but you can certainly relax that using these methods. So these 15,225 IID copies of these baseline covariates, which we'll call W. And here they consisted of age, sex, a patient's CD4 count before they started treatment, whether they lived in an urban or rural setting, et cetera. We also have our treatment. So they're observed for each patient, whether they were observed to start LREC immediately or not. And then finally their outcome, were they lost to care at 6 months? And here we're going to use, as you'll see in detail in the paper as well, we'll say that death is a failure. So if you're lost to care or died, then you're considered a failure. So that's our observed data. So then we also need to specify our statistical model. So as I said, what do we mean by a statistical model here? It's the set of possible distributions for our observed data. So in other words, we want our statistical model to reflect our true knowledge, and we want it to be big enough, to be a big enough set of distributions that we're confident that it actually contains the true distribution of our observed data. So with that, then we can talk about factorizing the probability distribution of our observed data into these 3 factors. And this is going to be important when we talk about different estimators, what they need to be, what things you need to do to implement them and what their properties are. So in particular, we can talk about just the distribution of W, the conditional distribution, so the baseline distribution of the baseline covariates, the conditional distribution of treatment given the baseline covariates. So in other words, the probability of immediate enrollment into LREC or not given your covariates. And then finally, the distribution of your outcome given your exposure and covariates. So in our case, the probability of being lost to care given whether you enrolled immediately in your baseline covariates. And we'll note that often our statistical model, if any, is only going to put restrictions on this conditional distribution of the exposure given covariates of the treatment mechanism. So in this next step of identification, I think this will be familiar to everyone, but it's nice to review it briefly in the point treatment setting before we extend on to the longitudinal setting. We need some sort of assumption in order to allow us to make progress in this process of translating our target causal parameter, so our average treatment effect or our expectation of the counterfactual outcome, into a statistical parameter or some parameter of our observed data distribution. Because if we do that, then we can make progress and get started with statistical estimation and inference. So a couple of assumptions are classically used to do this. One is the randomization assumption, which says that your counterfactual outcome is independent of your observed treatment given your baseline measured covariates. So a little bit more informally, this essentially just says that your baseline covariates are sufficient to control for confounding the effect of your exposure on your outcome. And in particular, we know that causal graphs can help us with this. And we know that this is going to hold if your baseline covariates W block all of the backdoor paths between your exposure and your outcome. Or in other words, if conditioning on these guys is enough to remove any possible association between your exposure and your outcome that's not due to the causal effect of interest. Because if that's true, then you can just adjust for these guys, and essentially within strata of your baseline covariates, you know that any observed association corresponds to a causal association. So this is the kind of basic identification assumption in terms of control for confounding. We also need an assumption that essentially says we have enough support in our data to be able to estimate our target parameter. And the second assumption sometimes goes by the name of positivity. So it just says we need some positive probability of, in our case, both being enrolled immediately and not being enrolled immediately, no matter what our covariate values are. So in our running case study, we're going to run into trouble with this if, for example, the sickest patients at baseline never enroll immediately. They're never actually enrolled immediately. And indeed, that's one of our motivations for saying when we do this analysis, we only do it among a population of patients who are by definition eligible for enrollment. Otherwise, we'd run into a problem here. Figure out how to move this guy up. There we go. So under these assumptions then, we have sort of our classical G-comp estimand, which I think people who've been following these workshops have certainly seen before, as well as people come from many different backgrounds. And that essentially, and what that says is that our expectation of our counterfactual outcome is going to be equal to, so this is a parameter of our counterfactual distribution, is going to be equal to the conditional expectation of the outcome given you got the exposure of interest and your baseline covariates. So the conditional expectation of the outcome given exposure and covariates, and then just standardized with respect to the marginal distribution of the covariates. So with that guy in hand, so here what we have here is a statistical parameter, a parameter of the observed data distribution. So now we can talk about three classes of estimator. So in particular, we're going to do a very brief review of propensity score-based estimators, in particular one type of those, the inverse probability of treatment-weighted estimator, which I think most people have seen. We'll talk very briefly about an outcome regression-based estimator. So an example of this is parametric G computation, and then talk about how essentially we can use kind of strengths of both of these guys and create a third class of estimator, the sort of so-called double robust or semi-parametric efficient estimators. And here we'll talk about a specific example of targeted maximum likelihood estimator. So first, the inverse probability of treatment weighted estimator. So the basic idea here is that we're going to estimate the treatment mechanism or the propensity score. So in other words, in our particular example, this is just estimating the probability that a patient enrolls in LREC immediately, given their baseline covariates. So classically in IPTW, this is estimated using, say, a parametric regression model, such as a logistic regression, sometimes including things like splines or other ways to try to make the model more flexible. And one potential pitfall of this approach is that this estimator's performance really relies on doing a good job estimating this propensity score or this treatment mechanism. And so if you use a misspecified parametric model to estimate that guy, you can end up with bias in your estimator and misleading inference. So with that guy in hand, then here's your most basic IPTW estimator. It just says, okay, let's take the people who actually got the treatment I care about. That's this indicator here. Let's look at their outcomes. But let's take the empirical mean of their outcomes, but we're going to weight them by the inverse of the probability that they got the treatment that they got. So in other words, if someone has an unusual treatment given their covariates, they're going to have a small predicted probability here, and they'll get a bigger weight. So essentially, one way that's sometimes taught is that we're reweighting to recapitulate what would look like if we'd done a trial in which, or we'd done an experiment in which people who were treated and weren't treated were balanced with respect to the observed covariates. This is the simple IPTW estimator. You can also do a stabilized counterpart of it. So this guy, in addition to needing to do a good job estimating the treatment mechanism, the IPTW estimator has another couple potential limitations depending on the setting. It can be high variance compared to other estimators, and it also can be unstable or biased in settings of strong confounding. And you can see why that might be, right? Because if you have a strong confounding, you end up in a situation where for certain levels of W, it might be very unlikely to get a certain level of treatment. So for example, patients who are sicker in our LREC example might have a positive probability of enrolling, but it might be very small. So if you get a small estimated probability down in this denominator, this weight can get extremely large, and it can lead to both high variance and essentially poor stability of the estimator or poor performance. So that's the quick intro to the IPT, or review of the IPTW estimator. So what about parametric G computation? So here what we do is we instead go after a different part of that observed data distribution. We just estimate the outcome regression. So in our case, this would be the probability that you're lost to care, given whether you enrolled immediately or not, and your covariates. So again, here, this is classically based on using a parametric regression model. So in our case, maybe a logistic regression. And here we run into the same problem in a different place. So once again, if we don't do a good job estimating this conditional expectation well, we can end up with bias in our final estimator as a result of that model misspecification. So we estimate this guy in some way. We're going to estimate the marginal distribution of W with the empirical distribution, and that gives us our parametric G computation estimator in the simple single time point setting that just says for each individual in our sample, we're going to take our estimate of this conditional expectation, use it to generate a predicted value at the treatment we care about, small a, for that individual. So use that individual's baseline covariates, and evaluate this estimate of the regression to predict what that outcome would have been if they'd gotten, say, small a is 1, so under treatment, or small a is 0, under no treatment, and then just take the empirical mean of those predictions. So with those tools in hand, we can move on to talk about what the targeted maximum likelihood estimator looks like in this simple single time point setting. So first, just a bit of motivation and overview for targeted maximum likelihood estimation. So the basic big picture of what we're going to do here is use machine learning to estimate the initial outcome regression and then update that initial fit in a smart way using the propensity score. So in particular, you could say, well, okay, one of the problems of parametric G computation is that we need to estimate this expectation of Y given A and W well. But it can be hard to do that in realistic data settings using an a priori specified parametric regression. We just don't know enough to write down a regression a priori to estimate this conditional expectation well. So then you might say, well, why don't we use some of these more flexible or machine learning methods to do that? And so we could do that, and we'll talk a little in the next couple slides, give a brief introduction to one approach you might use to do that, to estimate this conditional expectation of Y given A and W well. And so now you've got, say, a flexible estimator of this guy in hand. Why not just take that? And we saw on our previous slide, once we have an estimate of the expectation of the outcome given the exposure and the covariates, we have a simple way to just use that expectation to generate a predicted value for each subject under the treatment level or exposure level of interest and take the mean. So why don't we just take our estimate of this conditional expectation that comes from our machine learning approach and do the exact same thing. Just plug it in, generate a predicted value for each subject given their baseline covariates, and take the mean. Well, you could do that, but it turns out that this is not a great idea for inference. And that basically has to do with the fact that even if you're using or when you're using a flexible machine learning method to estimate this guy, the nice thing about that is that as your sample sizes increases, if you're being flexible enough, you're going to go towards the true conditional expectation of y given a and w. The problem is that you're not converging to that truth as fast as you would if you were using a correctly specified parametric model. And so if you just plug in that initial estimator, you're going to end up with too much bias relative to your variance to get reliable inference in general. So we'd kind of like to do another step here. And that's really one way of thinking about what TMLE does. It takes this, at least in this particular setting where we're going after EYA, it takes this initial estimate that can be generated with machine learning and then updates it to get a targeted estimate of this conditional expectation of y given a and w. Then once it has this targeted estimate, it's just going to do the same thing with that guy, generate a predicted value and for each subject under the treatment level of interest and take the mean. So why is it purple? There's color coding throughout this presentation. So it's purple because it starts out with this initial estimate of the outcome regression. I'm making these guys in red. But then it's going to target it making use of an estimate of the propensity score. So remember, this is the one we used in the inverse probability of treatment weighted estimator. And what's nice about this targeting step is it does a couple of appealing things. If this initial estimator of the expectation of y given a and w is not consistent, so not converging to the truth, it's going to reduce the bias even asymptotically, so even as n goes to infinity. It also is an opportunity to reduce the finite sample bias, the bias in the sample size you actually have, and also an opportunity to reduce variance. So the first step of this, as I said, is that we might want to use a flexible method to estimate this expectation of y given a and w. And one such method is so-called super learning. Excuse me, one sec. Thanks, sorry about that. So one such possible method is so-called super learning. So this is an ensemble machine learning approach that combines a few different, that allows us to combine different methods for estimating, in this case, the expectation of y given a and w. Has kind of a long history. So the basic idea of super learning for people who haven't seen it before is that we might have a bunch of candidate regressions that we think would work well for a given problem. So we might have, say, some different parametric regression models. Some of them have main terms only. Some of them perhaps have interactions between the exposure and the covariates. Some of them might include polynomials or, say, splines on some of the covariates. But we might also look at some data adaptive methods for estimating this conditional expectation of y given a and w, and there's lots and lots of data adaptive methods now out there. So the sort of issue is that going into a given problem, we don't necessarily know which of these approaches is going to give us the best approximation of that outcome regression or that conditional expectation of y given a and w. And so what super learning says is, let's actually just write down all of our competitors, all of our potential ways of estimating this expectation of y given a and w, and then let's use the data to choose between them. But let's use the data in a smart way that's essentially fair, that gives a fair measure of the performance of each of the competitors. On top of that, we're going to say, well, why restrict this competition to just the single best approach? Let's instead also allow these different algorithms to team up. So in other words, when we think about the possible approaches that we're going to look at, use the data to choose between to estimate the expectation of y given a and w, we're going to look at each of these candidates individually, but we'll also look at convex combinations of these candidates. So the final piece of this, though, is we say, okay, we want to set up a competition. We want to, in the competition, let the algorithms also team up, and then we want to use the data to choose the winner. But when we use the data to choose the winner, we want to be fair about it. We want to give an honest measure of performance. And so we don't want to use the same data that we're used to fit these algorithms, that the algorithms got to see when they were fitting the regression to judge their performance. And so there's lots of potential solutions to this problem, but superlearning makes use of this idea of v-fold cross-validation. So essentially we partition the data into folds. So in this case, there are 10 folds. We fit each of our candidate algorithms or each of our candidate approaches for estimating the expectation of y given a and w on 9/10 of the data. And then we evaluate the performance of each of these candidates on that left out 1/10. So we could do that once, but it turns out you have much better properties if you do it rotating through each of the folds. So in essence, what superlearner does is it says, okay, let's try out all my candidates on these 9/10 of the data and evaluate performance on the left out 1/10, but then let's rotate. Now let's train all my candidates on this other 9/10 of the data, leave out fold 9 and evaluate performance on fold 9. So we rotate through the folds, and once we've done this, each observation is served in the validation set, or the set that we use to evaluate performance once. So we get a better measure of the comparative performance of each of our candidates. And then we're going to use that, so average these performance measures across these validation sets, and then choose the algorithm or the team of algorithms with the best performance. So that gives us an approach to flexibly obtain an initial estimate of this outcome regression. Now, you could also obtain an initial estimate of this outcome regression using a parametric model. But the properties of this estimator are going to be driven by how good a job we do on this conditional expectation of the outcome given a and w, as well as how good a job we do on the propensity score. So we obtain this initial estimate of the outcome regression, for example, using superlearning. And then the next step is we're going to target or update that initial estimate. So what does this targeting step look like? So basically it just says, and this is on the logit scale, but I've just suppressed the logit to make it easier to look at. It says, take that initial fit, and the update is that going to be that initial fit plus some epsilon. And that will give us our targeted or our updated estimate of the expectation of y given a and w. So the key piece is how we fit epsilon. So what we're going to do, and there's various implementations of the TMLE algorithm, but I'm going to talk about a common and sort of highly effective one, is use maximum likelihood to fit this epsilon, where we essentially fit. So how is this actually implemented? It means, so we get our initial fit here, and then we take the second step in which we fit a logistic regression of our observed outcome on the intercept. So epsilon here is the intercept. We're going to use maximum likelihood to estimate that intercept, but using this initial fit as an offset. So essentially what we're doing is maximum likelihood here to estimate the residuals in some sense. But the key piece is we're also going to use these weights, where the weights involve the inverse of the propensity score. So what this says is when we fit that epsilon for the update, we're going to give some observations more weight than others. And in particular, we're going to give those individuals who have unusual treatments, given their covariate values, they're going to get small predicted probabilities here, and therefore big weights. So this should now seem familiar. This sort of concept should seem familiar from the introduction of the IPTW estimator. There's obviously quite a bit more formality to this. I mean, the basic idea is that the way that we've constructed this model, as well as the use of the weights, is going to ensure that fitting epsilon is going to solve the efficient influence curve estimating equation, and that confers all sorts of nice properties on this estimator. So once we've done this, we get an updated estimate of the conditional expectation of y given a and w. We just plug that guy in, just like we did for the GComp estimator, evaluate, so we take that fit, predict the outcome at the treatment level we care about, so say exposure or unexposure, and then take the empirical mean of those predicted outcomes. So this guy has, targeted maximum likelihood has a number of nice properties, and many of these are shared with other double robust estimators as well, of which TMLE is one example. So in general, the double robust estimators are nice because they're consistent, so they're going to converge to the truth as sample size goes to infinity. If either this outcome regression is estimated consistently or this propensity score is estimated consistently. So remember, for IPTW, we needed to estimate this propensity score or treatment mechanism consistently. And for parametric GComp, we needed to get this guy right, estimate the conditional outcome regression or the conditional expectation of the outcome given A and W. Here, it's consistent if we do either consistently. And that's what's sometimes referred to as the double robust property. It's also efficient in a very specific sense. So, and under conditions. So that means it's going to have the lowest asymptotic variance among reasonable estimators of the asymptotically linear estimators of this statistical parameter if we estimate both these guys consistently and do a reasonable job at it. Another nice thing about the double robust estimators is they have the potential to incorporate machine learning. So remember I said one downside of trying to use machine learning without the targeting step is you end up with too much bias relative to your variance for reliable inference. So what double robust estimators do is they give you a chance to incorporate machine learning in estimating both this outcome regression and this propensity score. You start off with a flexible estimate of this guy, and then you do this targeted bias reduction step that can restore a valid inference. That said, I mean, as is often the case, it's certainly not a guarantee. So we still need that the estimators of this outcome regression and propensity score are going to be converging to the truth fast enough. And then finally, a property of targeted maximum likelihood that's nice is that it's a substitution estimator or a plug-in estimator. So what do we mean by that? Essentially, that it takes exactly the same form as that GComp estimator. So it's just based on an updated estimate of the outcome regression, and we just plug in the updated estimate into really exactly the same, we're using the exact same form as the parametric GComp estimator based on our identification result. Why is that nice? As we'll see in a little bit, it can give us some improved performance in the setting of sparse data compared to some of the alternatives. So that is the introduction, I think, just to get ourselves into the causal roadmap thinking, as well as introduce these three classes of estimators and TMLE at a broad level. And we'll now, in this next step, go on to extend that using our case study again to a case where we're interested in the causal effect of multiple interventions or longitudinal interventions. Before I do that, though, I'll just show a quick update of, or just show an example of how you can use the LTMLE R package to implement what we've done so far. So the slides will be available after the talk, and you can link through those to LTMLE vignette that has these examples and many more sort of worked out in greater depth. But this is just to give a flavor of one of the R packages, of which there are multiple, that's available to go after these parameters. So here's an example where our data consists of baseline covariates, and then we're just showing the first three rows here just for illustration. So we've got a simple data example just to show you how to use this, where you've got one baseline covariate W, a binary A, and a binary Y. So you call the LTMLE function, tell it which the A nodes are. So what's the treatment? It's A. What's the outcome? It's Y. And then what's the treatment intervention? What's the counterfactual intervention on the exposure that you care about? So here we just say what we want is 0. So in other words, we're going after the expectation of Y 0, counterfactual outcome under no exposure. So that's the call, and it'll spit out a number of things. One of these is the TMLE estimator, implemented as I just described, a parameter estimate, a standard error estimate based on estimated influence curve, and a 95% confidence interval. You can also use the same package to output the IPTW estimator. So this is the stabilized IPTW estimator in this case. I showed the simple version just as a review. So again, you can get a parameter estimate, standard error, and confidence interval. And then just by asking for the IPTW estimator, and then you can also use it to output a parametric GComp estimator. Finally, you might not care just about the expectation of the counterfactual outcome under a specific treatment level. You might instead care about, for example, the average treatment effect. And so here we've modified this call to the TMLE function just slightly. So again, we have our exposure, our outcome, and now we say, no, I don't just care about one counterfactual intervention, I care about two. So I want to set A equal to 1, and I want to set A equal to 0. And so now when we ask for the summary, we've got, the package will output various output, including the additive treatment effect or the average treatment effect, a parameter estimate, p-value, and confidence interval for that. You can also output the relative risk or the marginal odds ratio. All right. So with that in hand, then, let us move beyond single time point static interventions, which I think is why many of you are on this call. But now we really have the tools in hand to talk about how to extend these methods to the longitudinal setting. So first, we'll talk about multiple interventions, the effect of multiple interventions focusing on static interventions. And then once we've done that, it's an easy step to make these dynamic. So back to our case study and our motivating question then. So remember we started off by saying what we care about is the effect of enrollment into low-risk express care, so enrollment into this nurse-based triage on retention. So we started off by saying, oh, let's look at the effect of a single time point treatment. So we could say, oh, let's focus on the difference in retention or probability of retention if all these patients eligible for enrollment in the program either enrolled immediately versus did not enroll immediately. So this is an effect of a decision or an action at a single time point. And there's nothing wrong with this in terms of it's a well-defined causal question, it has an interpretation, but it might not actually have the interpretation that you care most about. So in this example, why might that be the case? Well, okay, enroll immediately, that's fine, you enroll immediately. But what about this counterfactual Y0? This corresponds to a hypothetical intervention that just says, okay, don't enroll immediately. So don't enroll in that first time chunk, don't enroll in those first 90 days. But it leaves the rest of your enrollment history random. It doesn't intervene on that. And so when we talk about someone's counterfactual Y0, their retention status under an intervention to prevent them from enrolling in that first 90 days, that individual could still have enrolled after that first 90 days. They might have enrolled in the second time, the second 3 months, or the third 3 months. And so this guy, while reasonable, may not really be getting at the question that we're most interested in. So what if instead we wanted to know about the effect of enrolling immediately in this program versus never enrolling in this program? So now in order to get at that, we have to think about counterfactuals that are indexed by interventions at multiple time points. So for example, don't enroll in the first 90 days, and don't enroll in the second 90 days, and don't enroll in the third 90 days, etc. So our causal question is more complex. Of course, longitudinal observed data can also be more complex, and I'm sure various people on the call are feeling very unsatisfied with this baseline covariates exposure outcome. And that's good, you should be. So let's now start taking the first steps towards building more realistic or handling more realistic observed data structures. So we're gonna keep our discrete time scale here. And we're going to just make a couple modifications to the data we observed or data we defined before. So now for covariates, we indeed have baseline covariates, so age, sex, your CD4 count before you started treatment, just as we did in the previous example. But now we're also going to acknowledge that we have time varying covariates. So we don't just have information on patients at baseline, we also have information on them that's updated over time. So for example, their CD4 count, the marker of how sick they are essentially could change over time. What antiretroviral drugs they're on could change over time. They might become pregnant, for example. So we're going to use W sub T to refer to these covariates that include baseline covariates at W for W0, but also time varying covariates for T equals 1 to 6. Okay. So then we also have an outcome, YT. So this is just an indicator that you're lost to care or died by time T. So before we just had that at a single time point. Now we're going to really acknowledge that this is an outcome, repeated measures outcome, or a time to event outcome, if you will, working on a discrete time scale. We're going to have an exposure ET. So this is an indicator that you enrolled in this program by time T. So before we just looked at this, we called it AT, and we just looked at this in the first interval. Did you enroll immediately or not? But now we're going to acknowledge that we have this same exposure at multiple time points. Did you enroll in the first time interval? If you didn't enroll in the first time interval, did you enroll in the second time interval, etc.? And then finally, we're going to acknowledge the potential for right censoring. So in this case, what would right censoring look like? So our outcome here is lost to care or died, but we are saying you're going to be right censored if you transferred outside of you transferred to a clinic that's outside of our data set where this LREC program is not available. So a bit extension of notation then to handle this more complex longitudinal observed data. So we're going to group our data now into two types of nodes or variables. We can talk about the non-intervention nodes. So that's this YT, just an indicator that you're still alive and in care over time, or actually an indicator that you've died or been lost to care over time. And then this WT, which are these time-varying covariates. And we're going to use a bar over a bar to refer to the history of these non-intervention nodes. So L bar T refers to your whole history of survival and care, as well as covariates up to time T. We also have intervention nodes. And this is why I flipped from using A to E. So our intervention nodes here, these are the things that we care about intervening onto change to get at our causal effect of interest. And so in particular now we have two of these types of intervention nodes. One is our exposure. So that's whether or not you enroll in this nurse-based triage or not. And the other type is this right censoring. So we're here saying that the things that we care about intervening on are indexing our counterfactual outcomes, intervening on are both when you enrolled in the low-risk express care program, but also censoring in the sense that we'd like to intervene to prevent censoring. So prevent this transfer out to other clinics so we could see what happens to you if you had stayed in the same clinic. And again, we'll use the bar notation to refer to the history of this over time. So again, we observe about 15,000 copies of this data structure that consists of your survival and covariate history over time, and then your LREC enrollment and censoring history over time. And again, our observed random variable O has distribution P0. So just like we did, exactly analogous to what we did for the point treatment setting, we can factorize the distribution of our observed data into those two parts, the blue part and the red part. So here in the blue part, we've got the treatment mechanism. The only difference is that now we've got multiple treatment decisions over time, and so the treatment mechanism component describes the probability at each time point, t equals 0 to 5, that a subject is enrolled in the LREC program, given their past enrollment history and their past covariate values. So this is the analog to the simple treatment mechanism or propensity score in the point treatment case. And then similarly, we've got the conditional distributions of the non-intervention nodes. So this is analogous to the distribution of the baseline covariates W, and then the distribution of the outcome given exposure and covariates in the covariates W in the point treatment setting. And so this just says, again, we could think about this being a product over time points of the distribution of the outcome and time varying covariates given their observed past. And we're going to continue to work in a large statistical model that is going to restrict, if anything, only the treatment, possible distributions for the treatment mechanism. So exactly analogous to what we did in the point treatment setting. And that's going to come in handy when we talk about the estimators. Before we talk about the estimators, though, let's handle the other parts of our causal inference roadmap. So we need to define our target causal parameter formally. We've kind of alluded to it, but we haven't written it down yet as a parameter of the distribution of counterfactual outcomes. So let's look now at the intervention-specific mean. So what is it that we care about here? We want to look at the probability that you're lost to care or died by 18 months, so T equals 6, if you never enrolled in this program and your censoring was prevented, or if you enrolled immediately in the program and censoring was prevented. So let's just use the notation we developed so far to express that formally. So here we're just saying we care about your counterfactual in-care survival at time 6 under a hypothetical intervention to set your, oops, I'm sorry, that should be an E, set your enrollment to never enroll and prevent censoring. And so just for simplicity, we're going to use just the 0 bar as shorthand to refer to that longitudinal intervention. And then we're going to look to compare to that guy, we're going to say, okay, this is the probability that you're lost to care by 18 months if you never enrolled and censoring was prevented. But let's contrast that with your probability you're lost to care by 18 months if you enrolled immediately and censoring was prevented. And we'll use analogous notation, just Y6 with just a 1 bar to refer to that counterfactual regime. And so with these guys in hand, we can think about defining causal effects exactly analogous to our point treatment causal effect. So in particular, we might be interested in the average treatment effect, or the difference in the probability, the counterfactual probability that you're lost to care by 18 months if you enrolled immediately in LREC and were never censored and weren't censored or never transferred to another clinic, versus if you never enrolled in LREC and didn't transfer to another clinic. And that's this average treatment effect here. So analogous to point treatment, but now for a longitudinal regime, including censoring. So we've defined our data, we've defined our target causal parameter. We still need to do this identification step where we translate our target causal parameter into a parameter of the observed data distribution so we can dive into estimation. And so I think this concept is familiar to many who've been following this workshop series, but just to review it as motivation for why we need more complex estimators. I've shown here just a simplified causal graph. So I've simplified out the data structure that we talked about just to make it easier to look at. So here we have enrollment at time 1 and enrollment in time 2. And the causal effects we care about are the causal effects of both of these enrollment decisions. For example, don't enroll here and don't enroll here on your survival. So we have some baseline covariates that can affect enrollment, that can affect baseline enrollment, and can also affect the outcome. So these are kind of our classic confounders, but we also have these guys, and these guys are really the problem, at least for using a point treatment identification result. And the reason for that is that your health at time 2, we could imagine might affect whether you enroll in the LREC program at time 2. So maybe patients that become more sick are less likely to be assigned to a nurse at time 2. Patients who become more sick are more likely to die or drop out of care. And then, so this guy is really a confounder of the effect of enrollment at time 2 on survival. If we don't take it into account, it's going to look like it's these sicker people are going to be enrolling, and they're also more likely to die. And so if we just look at, if we don't adjust for that, we're going to have a confounded effect. At the same time, though, this health may have been affected by an earlier enrollment decision. So for example, the decision not to enroll in LREC here might actually affect what your health looks like subsequently. So we don't want to condition for this or adjust for this confounder using a classic approach, because we're going to essentially lose some of this causal effect we care about. And so that brings us to, or motivates our more complex identification assumptions, as well as leads us to a more complicated statistical parameter. And to estimate this more complicated statistical parameter, we're going to need more complex estimators, but building on the point treatment ones we've introduced so far. So in particular, the analogous identification assumptions are sequential randomization. We can also think of applying this backdoor criteria sequentially. So essentially for each intervention node, each exposure in sequence, we want to say, are the variables that come before that enough to block the backdoor path for that intervention node, for that exposure? So here for enrollment at time 1, we have that baseline covariates are enough to control for confounding, enough to block that backdoor path. And here for enrollment at time 2, we have that baseline covariates together with time updated covariates are enough to block that backdoor path. So we're applying the same concept, but just sequentially for each intervention node in turn. We also need an extension of our positivity assumption, or our assumption that we have enough support in our observed data. So now this is just gonna, it's same as point treatment. It says, but we just apply it to each time point in turn. It says for each time point, we need that the probability that you get the regime of interest is going to be greater than 0. So you have some positive probability of following the regime or the intervention history that we care about, irrespective of what your history has been up until now. So what your covariates are up until now. And so, and we're going to need this to hold for each regime that we care about here. So in our case, enroll immediately and don't be censored, and never enroll and don't be censored. So it's worth taking a pause here to think a little bit about, in this case study, what this guy means and why it might be important to choose these regimes or exposure histories you care about carefully. Okay, for enroll immediately, you could say, okay, I just need, you have some probability of enrolling immediately, regardless of what your baseline covariates are. And I've been really careful to define my target population at baseline as patients who are all eligible to be enrolled in this task shifting program. So I've included nobody in my target population that's too sick at baseline to be enrolled, that wouldn't even meet the criteria. So I've taken care of that problem for that baseline time point. And I've taken care of that problem for this, for a regime that says, let's look at enrolling people immediately. Once you enroll immediately, your subsequent probabilities of already having been enrolled are 1 by definition, and so you have this guy holds by definition. However, you can really run into trouble when you think about longitudinal regimes that look at delaying enrollment in the LREC program. So for example, we might say, well, what about a regime that says, wait for 6 months and then enroll in the program? Why might that cause us problems with this assumption? So the reason is that even though we defined at baseline all of the subjects in our population to be eligible for enrollment, so we by definition said that none of them are too sick to enroll, once we look 6 months out, some of them may have become so sick that they're no longer eligible to enroll. So conditional on their time updated health, this L bar T, they might, and conditional on not having been enrolled yet, so this A bar equal to 0, they might have no probability of enrolling at that next time point. And so that means that there are certain regimes here where we really could run into trouble. So certain longitudinal exposure histories where we really run into trouble with this positivity assumption. However, in our case, we focused on 2 specific regimes. One was enroll immediately. The other was don't enroll at all. And so if you notice, for don't enroll at all we need to say is, given you haven't enrolled already, no matter what your covariates are, you have some positive probability of not enrolling. So it doesn't matter if some people became too sick to enroll, that they still have a positive probability of following the regime we care about and continuing to not enroll. So this is an example from a case study, but I kind of can't emphasize it enough. It's really worth thinking hard about your identification assumptions. And I think we're used to thinking really hard about kind of confounding and time-dependent confounding and what variables are sufficient for that assumption to hold. But just a reminder to also think hard about your positivity assumption and what sort of regimes are actually supported based even on your a priori data, what types of longitudinal exposures are going to be supported in your data. So that then brings us to our estimators. So I think we are at the top of the hour. So I think what I'll do is, before I dive into our longitudinal estimators, let's take a 5-minute break. And then we will come back. I'll talk a little bit about With that, we have an hour left. I'll talk about extensions to these longitudinal estimators, extensions to dynamic regimes, and then we'll leave time for Q&A at the end. All right, 5-minute break. Thanks so much, Frank. No. I usually I'll just do like a big teaching thing online. I'll be done in an hour, and then I'll all day. I told you before, but I see. No. It's all totally good. But yeah, I'm just on break. All right. Okay. All right, so I think we should be good again. Window, yep, view, full screen mode. Okay, excellent. Oops, doop, doop, doop. All right, so before the break, we had gotten to the point where we had extended our identification assumptions to the longitudinal setting. And so under those assumptions, we can identify our causal effect with the analog, there we go, with the analog of that point treatment G computation formula we started with. And so what does that look like? Here we're focusing again on the expected, the probability of being retained in care at time point 6 under a specific intervention on either always or never enrolling in this LREC program and not being censored. And so what does that look like? That it's extremely analogous to the point treatment GComp formula. So in particular, we can look first at this inner expectation. So this is just the expectation of the outcome, the probability that you're either dropped out of care or died by time 6, given your observed exposure history. So given your observed exposure history was equal to the exposure history we cared about. So for example, given that you were not censored and you never enrolled, and then given your observed covariate history. So these guys are the ones where we say this includes baseline covariates, but also time updated covariates that might have been affected by early enrollment decisions. So here's our expectation of the outcome given covariate history and exposure history. And just like in the point treatment setting, we then wanted to standardize with respect to the distribution of the covariates. We do that same thing here. So we're summing over the possible covariate histories. But the thing that's changed is we need to be careful what distribution of those covariates we standardize to. And in particular, we want to standardize to their distribution, to the distribution that they would have had under the exposure history that we care about. So essentially, when we take this standardizing step here, we want to make sure that we don't lose any of the effect of early treatment decisions on the intermediate values of the covariates. And so that's what the longitudinal GComp formula does. I know Jessica Young in the next session is going to talk in, I think, fairly great detail about this longitudinal GComp formula and how it can be used as a sort of the basis of estimator of longitudinal static and dynamic regimes. So I'll just give a brief overview of that in this slide as preview to her workshop and also as a way of, again, building up to the TMLE. So just like in the point treatment case, we can think of a parametric G computation estimator that goes after just estimating the components of this G computation formula directly. So in essence, what this guy does is it just says at each time point, let's estimate the conditional distributions or densities of all of the non-intervention covariates. So the time varying confounders, as well as the outcome, whether or not you drop out of care or die, given the observed past. So we get a whole bunch of estimates of these guys, and then we can just plug them in to that GComp identification formula here to get an estimator of our counterfactual outcome under our longitudinal regime. So this is great, although a limitation, just as in the case of the point treatment setting, is that it relies on doing a good job on all these conditional distributions of the non-intervention factors. And there can be a lot of those guys once you get into lots of different time varying covariates and lots of time points. And so in the point treatment case, this was susceptible to bias due to essentially not estimating this, the outcome regression well. In the longitudinal case, that can be even more of a challenge because you've got to estimate so many of these guys well. Which brings us to our second class of estimator, our inverse probability of treatment weighted estimator extended to the longitudinal setting. So what does IPTW do? Again, it's exactly analogous to what it does in the point treatment setting. So here, remember, we can, in the longitudinal setting, we can separate our distribution of our data into the distribution of these non-intervention factors given the past and the distribution of the exposure given the past, or the intervention factors given the past. And this, again, is the treatment mechanism. So the treatment mechanism in the longitudinal setting just has multiple components, that's all. So what that means is, for the IPTW estimator, just as we had to estimate that treatment mechanism or propensity score in the point treatment setting, now in the longitudinal setting, we have to estimate it essentially at each time point. So in our case study, that means for each time point, we're going to estimate the probability that you enroll in LREC, given you haven't already enrolled. So remember, if you've already enrolled, then we know that your A is 1 deterministically. Once you've enrolled, you've always enrolled. But given you haven't already enrolled, we need to estimate the probability you enroll given everything we've observed about you up until now. And then remember, our A here has enrollment, but it also has this other component. So we also need to estimate the probability you remain uncensored, given your enrollment history, that you weren't censored until now, and your past covariates. So again, just as in the point treatment setting, we can classically do this with parametric regression models, but once again, we can run into trouble with this estimator if those models don't do a good job of estimating this treatment mechanism. So in other words, if we use a misspecified parametric model. Now, we've now got in our pocket, right, this idea that we could use superlearning, and indeed you can use superlearning or data adaptive methods to estimate the propensity score. And there's some nice work showing that that can actually improve things. That said, it really introduces challenges for inference, so reliable confidence intervals and p-values, just as using superlearning or data adaptive methods introduce challenge for inference if we just plugged in those estimates into our GComp formula. So final step before getting to the longitudinal targeted maximum likelihood estimator then is to note that you can actually take that complicated GComp formula and rewrite it instead as a series of iterated conditional expectations. And so this was an important insight of Jamie Robbins, I think originally from 2000, that by taking that GComp formula and rewriting it in this way, you can essentially make this an easier estimation problem or reduce the dimensions of the problem. So all we've done here is we've taken that inner expectation, it's just the expectation of the outcome, in our case, the probability that you've been lost to care or died, given your covariate history and given your exposure history. So say, given that you've never enrolled in LREC and you're uncensored, we take that inner expectation, but then instead of trying to estimate what the distribution of all the covariates would be under the exposure history we care about, so we can standardize to that, instead we take this different approach and we essentially iterate these expectations outwards. So this is just using the law of iterated expectations, and it says, okay, take that inner person, inner guy, and then at the first step, let's integrate with respect to the distribution of L5 under the intervention that A5 is A5. So in other words, we're gonna take this expectation of this inner guy, given now just the covariate history up till time 4, and given you followed your covariate and you followed your exposure history up until time 4. We keep doing that, moving outwards till at that last step, time 1, the resulting quantity only depends on your baseline covariates, and finally we just take the expectation of that. So why is this worth spending time on? It gives us a basis for alternative parametric G-computation estimators, but it's also extremely helpful for our double robust estimators. And the key, I think the key insight here is that by re-expressing that original parametric G-comp formula, we've reduced the dimensions of the problem. And so now what we've got is a series of conditional expectations instead of a bunch of conditional densities. And so these conditional expectations are regression objects, and it's going to be a lot easier for us to estimate them well. So that brings us to the iterated conditional expectations GComp estimator, which I introduced because it's really the basis of the longitudinal TMLE that I'm going to talk about next. So because we've taken that GComp formula and written it as a series of conditional expectations, that suggests a natural way of estimating those expectations. So basically all you do is you start on the inside, you start at the last time point, you say, I'm going to regress my outcome at the last time point on the past. So estimate the probability that I'm still retained and alive at the last time point, given my LRAC enrollment history, I'm not censored, and my covariate history. And then I'm going to generate predicted values for everybody in my sample by evaluating the fit of that regression at the exposure history I care about. So evaluating that fit of that regression at never enroll and don't be censored, for example. So this gives us now a new sort of pseudo outcome to use in the next regression. So we take the predicted values from the first step, and now we're going to regress these predicted values. We're going on to the sort of time-reduced path. So we're going to fit another regression. So now we regress these predicted values on the reduced history. Now we just look at the exposure history up till time 4 and covariate values up to time 4. Again, we generate predicted values, and then we keep going. So now these predicted values are going to be the outcome for the next time point, and we do another regression. We keep going until we get to the beginning, and then when we get to the beginning, our expectation is only random through the baseline covariates, and we just take the empirical mean. So finally, that brings us to longitudinal TMLE. And I will say, if at this point you're getting distressed that this seems like a lot of work to program, we are going to then look at the one-line call in the LTMLE package to do these things. So you can take that approach. It's nice because you've reduced the dimensions of the problem, but it still has this issue that we have to do a good job estimating those conditional expectations well, or those regressions. And so we'd like to have a double robust approach analog to the double robust approach that we developed for the point treatment setting. And so there's a whole history of these double robust ICE estimators dating back to Robbins 2000. And at the end of the talk, I provide not a comprehensive bibliography, but at least a start in some of these references. So in particular here, we're going to talk about the TMLE, analog to the point treatment TLE in this framework. And these properties really carry over from the point treatment TMLE. So this TMLE, targeted maximum likelihood estimator, is going to be double robust. So consistent if either of these iterated conditional expectations, these outcome regressions, are estimated consistently, or our treatment mechanisms. So these, the probability of treatment or exposure given the observed past at each time point is estimated consistently. Just like the point treatment setting, it's going to be efficient if both are estimated consistently at reasonable rates. Just like the point treatment TMLE, it can incorporate machine learning. So it has the potential to use flexible methods to estimate both of these guys while still retaining statistical inference. But again, it's not a guarantee, and I'll talk a little about that. And again, just like the point treatment setting, it's a substitution estimator. So it's based on, again, just plugging in estimates of those conditional expectations to that GComp formula. And so that can, again, give it better performance in sparse data settings. So what does the TMLE algorithm for this guy look like? So it's exactly analogous to the iterated conditional expectation GComp estimator, so that series of iterated regressions with just two differences. One, we generate the initial estimate of those conditional expectations or those outcome regressions with machine learning, just like we did in the point treatment setting. And then second, before we move on to the next step, before we move on to then taking that initial estimate, generate a predicted value, and then using that predicted value as a pseudo outcome to fit a new regression, we just add an update step. And the update step is exactly analogous to what we did in the single time point setting. And just like in the single time point setting, it uses an inverse propensity score based weights. So here it is just on a slide. Again, it's just like the iterated conditional expectation GComp estimator, but it's just adding this additional step at each of these regressions. So again, we estimate that conditional expectation of the outcome given the past, for example, using superlearning, and that's our initial estimate. And then we're going to update the initial estimate, just as we did for the single time point, using maximum likelihood to fit an intercept-only logistic regression with that initial fit as an offset. And again, just using inverse probability weights. Here again, we can estimate this treatment mechanism using machine learning methods. And so then we move on to the next step, use this, this is actually updated fit to generate a predicted value from the prior step, and then we update it again. And we just iterate through this till we get to the end. So really just a series of regressions, each with an update step, where the update step looks like it does in the point treatment setting. So not such a hard estimator, but nonetheless, nice to have a package to call. So I'll just now illustrate how you can use the LTMLE package to go after this, to implement these different estimators. So a bit of syntax, now that we're into complex longitudinal data. So a little syntax for the LTMLE package. These A nodes are what we use to tell the package that this is a treatment or an exposure node. So in our LREC example, this would be this indicator of whether you enrolled in LREC or not. Our C nodes are just censoring indicators, so if you have right censoring. So here in our LREC example, this was just an indicator if you transferred to a new clinic by time t or not. Our L nodes are our time varying covariates, so these are our WTs. And our Y nodes are, as you might guess, our outcome or outcomes. So here again, it's allowing for a repeated measures outcome or an indicator of being lost to care or died by time t. So with that syntax, let's actually just look at a simpler data structure to get a feeling for how you can call the package. And again, all of these examples are available in the vignettes that are linked to from the presentation. So here we've just showing the first 6 rows of a simplified data structure where we have a baseline covariate W, first time point intervention that's binary, a time updated covariate we're calling L, a second intervention that's binary, and then finally a binary Y. And so here's the call to the package, just building on the point treatment call. We tell it, we give it our data. We tell it what our exposure nodes are, A1 and A2. We tell it what our time varying covariates are, here L. We tell it what our outcomes are, here it's just Y. And then finally, we need to tell it what is the regime we care about. So here we're saying what we care about is an intervention to set A1 to 0 and A2 to 0. And then it just returns the TMLE estimate based on the algorithm I just described. So what about right censoring? So now I've just expanded that out slightly and added an interim right censoring node here. So the only modification to the call is that we're going to, in addition, indicate that just tell it that they're right censoring node C. And the package by default assumes that if you tell it that C is a right censoring variable, then what you care about is the effect of the intervention in the absence of censoring. If you don't want to treat a variable that way, don't call it a right censoring variable. Finally, you can use the package, so the default of the package is just to fit main term logistic regression to estimate G and Q using the full past. But that is by no means, as we'll talk about in a second, the best idea or the only idea. And so instead, you have the option to call superlearner for the package, and you just do that by specifying superlearner library. You can call a default library. So library just means which algorithm should the machine learning package consider, or you can specify the library yourself. And then finally, just as for the point treatment setting, you can use this not just to look at the expected outcome under one regime, but actually to contrast expected outcome under different longitudinal regimes with inference. And so here's comparing intervention to set A1 to 1 and A2 to 0 versus A1 to 1 and A2 to 1. And we can get out the estimate in treatment estimate, so that's the first regime, the estimate of the expectation of the counterfactual estimate in the second regime, as well as additive treatment effect, relative risk, and odds ratio if you want it. So all well and good, and we've got this package and you can just call it easy peasy. Actually, no free lunch, and longitudinal problems are hard. High dimensional problems are hard. So I just want to talk briefly about a couple of the challenges that really do come up, and as well as things to keep in mind. So the first is that yes, it's great so you can estimate that outcome regression, that initial fit, and you get a chance to improve that fit at the second targeting step. But you really need that the initial fit of that regression not be too overfit. So you can't just sort of throw caution and thinking to the wind and run this as a black box, because if you overfit your initial regression, you're still going to run into trouble. And so there are ways of actually relaxing that condition a little bit that involve internal sample splitting that I won't talk about now, but aren't actually implemented in the TMLE package yet. So really, if you're using this package, you need to be careful not to overfit your initial outcome regression, which is good practice just in general, I think that people are familiar with. But it does mean that you should be careful of the default in the package. So this package is really not designed to be ironclad without sort of thoughtful user input. And so the default here is just a logistic regression with all past variables as main terms, and that might be a bad idea, both because it's not a good fit and also because it may lead to an overfit. And so if you do want to take this pathway of using a parametric regression for your treatment mechanism and your outcome regressions, then just be careful to specify what that model looks like carefully, and the package allows you to specify it however you want. And also, if you have a big history, consider some a priori knowledge-based reduction in your adjustment variables. So for example, you might only want to use the most recent values of your time-varying covariates, or you might want to do like a pre-screening step where you look at marginal associations of your time-varying covariates with your outcome. And some of those are discussed and illustrated in the paper that was distributed. The second challenge I just want to make people aware of is you know, we kind of introduced this by saying, well, one nice thing about these methods is that you can use machine learning approaches to estimate your propensity score and use machine learning approaches to estimate your outcome regression. And that's a nice property of double robust estimators, but it's not a guarantee. And so you still, if you want to use these machine learning approaches, you still really want your super learner, whatever approach you're using, to do a good job estimating both the treatment mechanism and the outcome regressions. And we need this, in particular, we need whatever estimator we're using here to converge to the truth fast enough. So this isn't such a condition if you have, for example, a randomized control trial, because in that case, we can always estimate the treatment mechanism extremely well because we know it. But it does, in observational data, become a real challenge. And sort of ensuring that the machine learning approaches we use converge quickly enough. And this is just, you know, it's an important area of, I think, of current research, and just to highlight some work that's making progress on that front. It also means, just practically speaking, that you should be careful in choosing your machine learning library. And in the addition to the two papers posted for the workshop, would just refer people to also as a recent paper by Schumacher et al. Talking about sort of library selection. Finally, a challenge of these estimators is the so-called practical positivity violations. So we talked about the need for just an assumption that you have some positive probability of following the exposure that you care about at each time point, irrespective of your past. Even if you have that, though, you can run into trouble, and you can particularly run into trouble with multiple time points. So why is that? So say you do have some positive probability of following the exposure we care about at each time point given the past, but it's small. So for example, say you have a small probability of not enrolling given you're healthy at each time point. That's small for a given time point, but once you start taking a product over 5 time points of small things, the product can get very small. And so you end up with these, again, these sort of large inverse weights that can cause problems. There are some partial responses to this. These are all defaults in the package. So one, as I'll show in a second, is these substitution estimators. So GComp and TMLE tend to perform better in those settings. You can also use a better variance estimator, and that's the default in the package. And then in particular, you want to bound your estimate of the treatment mechanism away from 0. Again, the package does that for you automatically. For those people familiar with IPTW, it's the analog of thinking about truncating your inverse probability weights. So some simulations and some data. So this is just an example. This is, again, in one of the papers that I referenced. You can get all the code of using, in this case, correctly specified parametric models to estimate those iterated outcome regressions and the treatment mechanism, just illustrating that your choice of estimator really can make a difference. So we're plotting here the mean squared error of the estimator, and I'll just focus on the 3 estimators we've talked about in this session. So at the bottom here, this is the iterated conditional expectation GComp estimator, and it's great. And in general, that's what we predict by theory. So if we can use correctly specified regressions, this guy is going to be fantastic and unbeatable. The real reason to move beyond that is that often we can't. And once we get into machine learning approaches, inference becomes a problem. So, okay, what about IPTW? So I'm showing the IPTW estimator here in green. So you can see at the beginning time point, all the estimators are doing quite well as predicted by theory because they're all using correctly specified models. So IPTW here is using a propensity score based on a correctly specified model for the treatment mechanism. But as you move forward in time, those positivity assumptions become worse, or the denominators of the weights are going to get smaller and the weights get bigger, and you see the MSE of the IPTW estimator really blowing up. And then here's the TMLE hanging out down here. So indeed, it does a little bit worse than GComp, but still sort of retains better performance in the setting of these positivity violations. And then finally, just a snippet of results from this motivating case study. So here's an example using those data of applying 3 different estimators to estimate over time the probability of remaining alive and in care under enroll immediately in green and never enroll in blue. And so what you see when you look at this is just a simple unadjusted estimator. So where it looks like patients who enroll immediately do quite a bit better, but remember we're worried about confounding in the sense, so patients who enroll immediately do quite a bit better than those that never enroll. But remember we're worried about confounding in the sense that these never enrollers may actually be the sicker people. There may be a reason they're never enrolling, it's because they're becoming sick. And so here you see IPTW, in this case doesn't move the estimates very much at all, whereas TMLE really bumped up this never enroll survival curve, which is what you would, we don't know the truth because it's real data, but it's what you would expect if confounding is sort of working in the direction that we think it is. So let's now move beyond multiple time point interventions. So I think we have about 10 minutes, which is just about right, to talk about how we can now take these same concepts, same identification results, and same estimators and apply them to dynamic regimes. So a teeny bit more motivation. So we're still sticking with the problem of retention in HIV care in Africa, and what can we do to help people stay retained in care. So now that we're going to pivot our case study a little bit and talk about, in particular, how we could use dynamic regimes or adaptive treatment interventions to do a better job supporting people in staying in care. So this is just a bit of motivation here, which is to say that HIV-positive persons face a number of diverse barriers to being retained in care, and they range from structural barriers, so transport is too expensive, to psychosocial barriers, so maybe problems with patient and clinic interactions or dissatisfaction with care, to medical reasons. So maybe they're too sick to travel. So what does that mean? It means that any one-size-fits-all approach is likely to fall short. So in particular, there's several behavioral interventions that have proven efficacy in the setting of, to improve retention in care compared to standard of care. So we could think about using SMS text messages that provide appointment reminders that also sort of are a way to engage with patients from a distance. We could think about travel vouchers or small conditional cash incentives for making on-time visits. And we could think about peer navigators, so essentially providing relationship-based support for overcoming barriers to care. So the hypothesis is that because there's such diverse barriers and people drop out of care for such different reasons, there's no one of these that's going to work best for all types of patients. And so given that, we think that using any sort of one-size-fits-all approach, or in counterfactual terms, a static approach where we say what's the effect of giving everyone an SMS versus everyone's standard of care, is going to fall short in the sense that it'll be inefficient. There's lots of patients who might do well with just standard of care and they don't need an intervention, which is important in a resource-limited setting to figure out who those people are, but also suboptimally effective. So some patients, even if a navigator works best on average, some patients might still have done better if they got a voucher. So this then motivates our questions about dynamic regimes. So we want to say, can we improve effectiveness and efficiency by targeting interventions based on individual characteristics? And that's exactly what a dynamic regime does. It's a rule for assigning or modifying an intervention based on an individual's potentially changing characteristics. So we could think about different types of target causal parameters in the setting of dynamic regimes. One is, for example, the expected outcome under a specific dynamic regime. So in other words, the mean outcome if all subjects had followed some rule. We could think about an optimal dynamic regime. So what rule would result in the best mean outcome if all subjects followed it? And then we could think about what would the expected outcome be under that optimal regime. So what's the mean outcome if all subjects had followed an optimal rule compared to some simpler alternative, for example? And so to be concrete, this is just an overview of the ADAPT-R trial that I co-PI with Dr. Alvin Gang. And this is what some people may have heard of as a sequential and multiple assignment randomized trial. And so I introduced this here because I know many people work on observational data and not on randomized trials, but everything you learn from the context of a sequential multiple assignment randomized trial in terms of identification assumptions and estimators can also be applied to the observational setting. The only difference is, as usual, when you move from an experiment to observational setting, we have to make untestable assumptions about confounding. So here in this trial, then, we have 1,800 HIV patients initiating ART in Kenya, and we wanted to develop and evaluate dynamic regimes to help them stay in care. So the basic study design is that patients who are starting care are first randomized to a first stage intervention, so either standard of care, education counseling, SMS text messages, or vouchers. And then we assess early response, so whether or not they're retained in care or not at 1 year. If they are retained, then if they're on an active arm, they are randomized to continue or not. If they're not retained, so if they drop out of care, then they're randomized to essentially an escalation, either standard of care outreach, a combination of SMSs and vouchers, or a navigator. And then we measure the outcome at the end of 2 years. So back to our causal framework, what do the data look like in this case? We have some baseline covariates, and we can look at patient wealth and satisfaction with care. We have a first-line intervention. Here it's SMS, voucher, education. We have some time-varying covariates. And in particular, this includes, say, a patient's updated satisfaction with care. So how satisfied are they feeling, which might have been affected by what first-line intervention they got, as well as did they fail in the first year? So were they 14 days late for a visit within the first year of follow-up? Then we have a second-line intervention that says if they fail, that second-line intervention is either SMS and voucher, navigator, or outreach. And if they don't fail, then they either continue or stop their first-line intervention. And then finally, we have a final outcome, viral failure at year 2. Again, we're continuing to make work in a statistical model that makes assumptions only on the treatment mechanism. And here, in particular, we have knowledge about the treatment mechanism because we actually know how that first line intervention was assigned, it was randomized, and how that second line intervention was assigned. It was randomized conditional on failure. So with that as a framing then, we can talk about specific target parameters. So in particular, we could talk about decision rules. So at each time t, a decision rule dt is going to assign some intervention value, enroll or not, censor or not, in the context of LRAC, or here, for example, what retention intervention should you get based on your observed past. So then we can look at a dynamic regime. So all that is a set of rules, one for each time point. So here in the ADAPT-R example, we could say, let's look at a simple rule that says, give SMS at ART start. And then if you're 14 days late, so if your Y1 is 1, then escalate to a peer navigator. Otherwise, just stop the SMS. So that's a particular rule. And then we could ask about the regime-specific mean. So the expected outcome under that particular regime. So identification and estimation, we can leverage everything we've learned so far. The identification assumptions are very closely analogous to what we did for the longitudinal static regime. And they are going to hold by design in a sequentially randomized trial. That said, you can still assume them in observational data. And then our estimators, again, are going to be exactly analogous to those we just built up for the longitudinal static regime. So we've got a GComp estimator, including ICE. We've got an IPTW estimator, and we've got an LTMLE. And the only thing we change is we just evaluate, instead of evaluating for a specific static regime, small bar a, we just evaluate for whether someone's observed treatment history corresponds to following the regime that we care about. That's the only modification. And so what about implementing this in the LTMLE package? Again, it's a very small modification. So here, working again just for illustration with a much simplified data structure, we have baseline covariates, a time-varying intervention, an intermediate covariate, a second time-varying intervention, and an outcome. You just need to decide what your regime of interest is. So here, for example, let's say the regime of interest is always treat at time 1, and then only treat at time 2 if your intermediate covariate is greater than 0, for example. So the only modification you have to make when you call the LTMLE function is you just have to tell it for each individual what they were supposed to follow given their covariates. So this first step, we're going to define the regimes of interest by saying, okay, for each individual, we're going to tell it what intervention should that individual have gotten at A1, here it's 1, and what intervention should that individual have gotten at time 2, and that's just this function that says if L is greater than 0, it should get a 1, otherwise get a 0. And that's it, and otherwise it's the exact same call to the function, and you can output all the types of output that we looked at already. So I think given that, I was a little bit on the fence whether we'd have time for optimal dynamic regimes, and I think we do not, which is totally fine. I think given that, let me just conclude with a couple of thoughts. So first is that you can use all of these estimators in observational setting, but actually even in an RCT setting, using these approaches can improve your efficiency, and that's all that this graph is showing here. And then just to summarize then a few key points, and we will move to the Q&A. So we've covered a ton of ground, but I've been trying to put this talk together. I just felt like it was going to be better if I started with the basics and built up. So just to kind of review briefly where we've ended up, we've talked about, in particular, these double robust ICE estimators, which I think are kind of an underappreciated class of estimators in general. And in particular, we talked about this longitudinal TMLE estimator. So we can use this to go after the regime-specific mean for either dynamic regimes or static regimes. We didn't talk about it, but you can also use this approach to go after marginal structural model parameters, including dynamic marginal structural model parameters, optimal regimes, and expected outcomes under optimal regimes. When using this, as we saw in observational data, is a potential to reduce bias and variance, and in sequentially randomized trials, the potential to reduce variance. We also, though, saw the challenge of practical positivity violations, and really, I can't say enough that these are ubiquitous in really observational data settings. There's been a lot of progress in handling this problem, but it's still a major concern. That said, I would say that these methods didn't create the problem. They really kind of just bring the problem up to the forefront and bring it to your attention. The underlying problem is really a problem of support in the data for some of these more complex regimes. And then finally, we didn't talk about it today, but these methods can really be extended to look at optimal dynamic regimes. Just a couple pointers to the functionality of the LTMLE-R package. It has a bunch of functionality we didn't talk about today, can handle hierarchical data in some ways. You can also use it to go after controlled direct effects, for example. And we talked about much of this other functionality. And so I think with that, I will just conclude with some acknowledgements. Really all of this is joint work with Mark Vonderlaan at UC Berkeley. And also all of this LREC work was done with Dr. Lynn Tran, formerly of Berkeley and now at Google. A big acknowledgement to the patients in the low risk express care study, to AMPATH, as well as my co-PI in ADAPT-R, Dr. Elvin Gang. Joshua Schwab is the lead developer on the LTMLE-R package, and that was initially funded by the International Epidemiologic Databases to Evaluate AIDS, and our sponsors, PEPFAR and the NIH. So with that, I will stop my screen share and take some questions. All right, and Yi, I know I said that I was gonna handle the questions, but I'm realizing this format, it's gonna be really hard to go through them. Is there any way that you could shoot me some questions? If not, that is fine, and I will just read over here.
Okay. Did you unmute me? All right. Okay, the first question is from Xin Feng. The question is, Since TMLE is so good, then is there still role for other estimators?
I love that question. That's a great question. So this is something that I really have, I struggle with presenting this because TMLE really does have nice properties, but it's not magic. And I think, I can't emphasize that enough. So I think the short answer is yes, there's room for other estimators. Yes, there's room for further work. Is it possible to break it? Absolutely. So I tried to highlight a couple of the ways in which TMLE can break, like really you run into trouble. One of them is that you kind of use it as a black box approach and don't give a lot of thought to estimating either your propensity score or your outcome regression. Although I will say that that will equally land you in trouble if you don't give a lot of thought to those guys and you use other estimators. So that's kind of a blanket caution. Positivity violations in longitudinal data are real issues, and you run very quickly into these small predicted probabilities with big weights, and it really can influence your the performance of your estimator. So in those simulations I showed you, they weren't rigged to show that by any means. That was just what they spit out, where TMLE was really doing quite well. But it's certainly possible to come up with situations where it really does not do well. And that can particularly be true when you look at the performance of the variance estimator. You can get anti-conservative variance estimates. Although I will say that's also very much true for IPTW, so that's not a TMLE specific problem. Something to be aware of in the R package is that the default variance estimator is essentially doing a TMLE of the variance to try to get around this problem. And so what happens there is that it will give you good confidence interval coverage when you've got enough support in your data. And what it's designed to do is once you get not enough support, it'll just blow up. It's not going for nominal coverage anymore. It's going for like a red flag to say, you've got a serious problem here, don't trust this confidence interval. So that's the default in the package, which should help protect a little bit, but is there room for additional approaches? I mean, I think absolutely. Lots of exciting areas of research. Another one is, how do we come up with machine learning estimators that are flexible enough to allow us to actually estimate those propensity score and outcome regressions consistently with realistic data settings, but also kind of ensure these properties we want to have good statistical inference. And I'd say that's another very exciting area of current research. So, is TMLE the answer to everything? No, there's definitely ways to break it. You can run into trouble. I think maybe my final note on that, which is just a plea to when you're doing any sort of applied data analysis, it's really good to set up a simulation that looks like it and try out the different estimators because you'll get at least an idea of where you may be running into trouble.
The second question, can you give us another example publication that used LTMLE package with user-defined regression models and didn't use the default?
Yes, absolutely. So there's the Lin Tran ones I showed. There is Michael Schumacher, which I referenced. It should be in the slide references. There is, I don't think, but I can't actually remember, which is embarrassing, but I don't think there's Noemi Kreif has a paper in AJE using LTMLE, and I don't think she used the default for Superlearner. And there is, I believe that reference is in the references, but I will add it if not. So in short, yes, there are absolutely, I'd say a number of examples. I kind of decided to pick this case study because I thought that Lynn did a nice job of really sort of diving into the intricacies of using Superlearner in these settings. And he gives kind of a lot of the kind of nitty gritty of it as well as gives all the code. But there are a number of applied examples.
Next question is from Doug. First, thank you for a fantastic and comprehensive talk, and I apologize if I missed this. I had to step out for about 20 minutes after the break, but I didn't see anything about statistics to check covariate balance. Example, forest plots of the standardized means. Our experience with point interventions and the propensity score-based methods is that it's often unpredictable which assignment model approach will best balance covariates. It seems like a poor approach to just try a whole range of methods within reason and check balance of each. But I wonder if there is some value to that approach. I would like to hear how you check balance in the time-varying and dynamic treatment settings. Thank you again.
So that's a great question. I mean, I think the short answer to that question is that covariates are not all created equal in terms of how important balancing them is. And so you could have, a very strong confounder that it's sort of crucial to achieve balance on. And you can have the extreme version is you could have an instrument, so a variable that predicts your exposure extremely strongly, but isn't actually a confounder at all or doesn't predict your outcome. And so that if you try balancing on the instrument, or even just try adjusting for that instrument, because that's essentially what we're doing here, that you can actually hurt yourself. And so I think that's one motivation to kind of step away from an approach where the measure of how well we're doing is to look at balance metrics, and instead move to an approach that says, because essentially what this is, that's another interesting area of research, instead moves to an approach that says, let's try to really focus on what matters most for the target parameter, right? So for the actual parameter we care about, in this case, the average treatment effect. And I will say maybe one other note on that topic, which is an interesting one, which is kind of beyond the scope of this talk, but I think another important class of these estimators are the so-called collaborative TMLEs, or collaborative estimators, where they try to really kind of get around or tackle that problem from a different dimension, in the sense that you first fit this outcome regression, and then you only want to put things into your propensity score at that second stage that actually improve things beyond. So beyond the adjustment that you got from adjusting for your covariates and your outcome regression, you kind of only want to additionally adjust for things in your propensity score that help you for your target parameter. And so that's also, not in this talk, but kind of, I think, an important way of thinking about how we navigate this problem of you cannot in reasonable dimensions balance everything. And you can quickly run into sort of support problems. And so how do we kind of figure out what's most important for the target parameter?
The last question. Do you know of applications of this method to retention in opioid treatments? This question is from Email Coleman.
I don't, but it should definitely extend. I don't. I mean, I do know that there has been a fair amount of work in sort of the addiction research on using SMARTs, so addiction research, mental health, on using these SMARTs, or these sequential multiple assignment randomized trials. And so that's not so much retention, but I do think that there's been a fair amount of longitudinal causal methods, and in particular dynamic regime methods, in the sequential randomized trial setting. That said, like as I noted, all of those things really, there's no reason they have to be restricted to the randomized trial setting. They can be extended out to the observational setting. And I think retention problems in general are, especially when you're interested in kind of longitudinal effects and their effects on retention, I think are often candidates where you will run into this problem of time-dependent confounding, and you probably do need to go beyond the kind of classic static or single time point methods in order to be able to do a good job going after the effects on that. So it seems to me a ripe area. Yeah.
Okay, Maya, that's all the questions that we have. You addressed all of them.
Oh my goodness, I'm right on time. It's amazing.
Amazing.
Thanks, everyone. This is really a nice question. Thanks so much, Yi and PCOR, for hosting this. And I would say my only sadness is it's much more fun to meet people in person. But the reach outweighs that. But please come visit us in Berkeley if you are ever out that way. And I would say any questions, the other piece I would say is any questions about the package, you should also feel free to email Josh Schwab, who's the lead developer, and his contacts at the in CRAN. So
great, fantastic. Thank you very much, Maya.
Thank you very much. Bye.
Bye-bye. Coming up next, April 24th is our workshop number 3. Mark your calendar, April 24th, 11 to 1 p.m., right? Eastern Time. Thank you all very much for participating. See you next time.